Welcome back to our exploration of quantum mechanics. In our previous episode, we discussed the foundational contribution of Max Planck and his work on black body radiation. Today, we delve into another two groundbreaking discoveries, the explanation of the photoelectric effect and Bohr's atomic model. Let's begin by examining the photoelectric effect. As we explore the explanation of the photoelectric effect, let's rewind to the late 19th century, when German physicist Heinrich Hertz made a fascinating observation. During his experiments with electromagnetic waves, Hertz noticed when EM wave strikes a metal plate, sparks were emitted. The emission itself wasn't entirely surprising. What fascinated scientists was the peculiarities associated with this phenomenon. They discovered that different metals required bursts of light with specific minimum frequencies called threshold frequency for electron emission to occur. Increasing the intensity of the light resulted in a higher number of emitted electrons, but without altering their energy. On the other hand, increasing the frequency of the light led to electrons being emitted with higher energy, but without a corresponding increase in the number of electrons produced. This puzzle became widely recognized as the photoelectric effect. The wave theory, which described light as a continuous wave, was unable to provide a satisfactory explanation for the photoelectric effect. According to wave theory, the energy of a wave is determined by its amplitude or intensity. Therefore, increasing the intensity of light should increase the energy transferred to the electrons, leading to higher energy emissions. However, this was not what the experiments showed. These discrepancies between the predictions of classical wave theory and the experimental observations of the photoelectric effect led to the realization that a new understanding of light and its interaction with matter was needed. In 1905, Albert Einstein, based on Planck's quantum theory, published a seminal paper that provided a groundbreaking explanation for the photoelectric effect. Building upon Planck's work, Einstein proposed that light behaves not only as a wave, but also as discrete particles of energy called photons. He proposed that each photon carries a specific amount of energy directly related to its frequency. When photons collide with a metal surface, they transfer their energy to the electrons present in the material. This energy can be divided into two distinct components. The first portion of energy is utilized to overcome the binding forces that hold the electron within the metal. This amount of energy is known as the work function of the metal and is proportional to the threshold frequency. Once the electron is liberated from the metal, the remaining energy is imparted to the electron as kinetic energy. Increasing the intensity of the light simply means more photons are striking the surface, releasing a larger number of electrons, while the energy of individual electrons remains the same. Conversely, increasing the frequency of the light means that each photon carries more energy, resulting in electrons being emitted with higher energies. But the overall number of electrons remains constant. Einstein's work not only confirmed the particle-like nature of light, but also contributed significantly to the development of quantum mechanics, further solidifying the quantum theory established by Max Planck. This was the short story of the photoelectric effect. Now let's move to the atomic model proposed by Niels Bohr. One of the most significant experiments in modern physics involves the study of how atoms absorb and emit light. The exploration of this phenomenon began with a groundbreaking model proposed in 1910 by Rutherford, who proposed that atoms consist of a massive nucleus with a positive charge and electrons orbiting around it. This model provided a crucial first step in understanding the absorption and emission of light by atoms. However, classical theory posed a challenge to this model. According to classical theory, the electrons, due to their angular acceleration, would continuously lose energy and eventually spiral into the nucleus in a relatively short period of time. In 1913, Niels Bohr proposed a model that not only resolved the dilemmas, but also explained the discrete nature of the spectrum. Bohr's model was based on the following assumptions. Electrons exist in specific stable circular orbits around the nucleus without giving off radiation as predicted by classical theory. Electrons can transition between these orbits, gaining or losing energy equal to the difference in energy levels. The angular momentum of an electron in an orbit is quantized, meaning it can only take on specific values that are integral multiples of Planck's constant divided by 2p. The centripetal force required to move an electron around the nucleus is provided by the electrostatic force between the nucleus and the electron. Using the two equations, one can find the radius of a particular orbit and the energy of electron in that orbit. For hydrogen atom, the energy of nth orbit is given by. The negative sign in the relation indicates that the electrons are bound to the nucleus. Also, because of the square term in the denominator, the energy reduces as the electron moves away from the nucleus. Bohr proposed that when an electron in a higher energy level transitions to a lower energy level, it releases energy in the form of light. Depending on the energy level where the electron finally reaches, the emitted light corresponds to specific wavelengths or colors, giving rise to a series of distinct spectral lines in the hydrogen emission spectrum. The quantized nature of electron energy levels in the Bohr model paved the way for the development of quantum mechanics. It hinted at the existence of discrete energy states, challenging the classical view of continuous energy. With this, we conclude this video. Thank you for joining us today and stay tuned for more exciting discoveries ahead.